Sauce here. This is a video lesson on the rectangle method for area under a curve. We're going to begin with notation that stands for and ask the question, what is the area under the function x squared on the interval from 1 to 3? And in order to organize an estimate to calculate that area, I'm going to make a table. And my table is going to begin with choosing values of x and using the function x squared to calculate values of y. Or f of x. I'm going to start with the first value of x being my lower bound of 1. And when I do, I will get a function value of 1 squared, which is 1. I'm going to make a large and well-organized graph. I'm going to choose 2 boxes to equal 1 unit on the horizontal axis. I need to go from 1 to 3 to produce the interval. And I'm going to choose 1 box per 1 unit on my vertical axis. So my first point is at 1, 1. If I've chosen 2 boxes to be 1 unit on my horizontal axis, then I would put in values of 1.5, 2, 2.5, and 3 to keep organized with how I chose my graph. At 2, the function is 4. At 3, the value of the function is 9. I can plot those points here, and 3, 9. The graph is quadratic. It's a curve that is the parent parabolic curve, but I've made it large in order to show my work, to show my process. If I put 1 and 1/2 into the function, I get 2 1/4. And if I put 2 1/2, 2 1/2 squared is 6 1/4. The method I'm going to use to estimate the area under the curve is choosing rectangles to divide the area of this region, because rectangles are easy to calculate the area of. The formula is simply base times height. So I'm trying to find the area between the function and the x-axis. And I'm going to do it by separating the interval into 4 equal partitions, such that each partition, each base of the rectangles that I'm creating have a measure of 1/2. And I could call that delta x, or change in x, because to go from one side of the rectangle to the other, I change x by 1/2. That's the base of the rectangles. And the heights of the rectangles are going to be found at function values. If I draw vertical lines at each of these locations, then I've drawn the sides of my rectangles. The heights of the rectangles will be established at function values. So this value here of the function, or this point 1, 1, if I draw a small horizontal line to represent the height, then it creates a rectangle whose height is a function value and whose base is delta x. I can draw 4 rectangles. These 4 rectangles is a portion of the area between the function and the x-axis. And if I shade those rectangles, I can see that they produce a method for estimating the area under the curve, but it's going to be an approximation because the area that is shaded is not exactly the area under the curve. There's always an extra amount of area above each rectangle but below the curve that is not accounted for when I add the rectangles up. This space that is the difference between the exact area and the estimate is called the error. So I know that the sum of these rectangles is going to produce an underestimate because I can see that the error is an amount of area that is not being accounted for. But I'm going to approach my estimate this way and continue creating my table to organize the area of those rectangles and then later sum them up. I'm going to put another column in my table that will represent delta x, the base of every rectangle. And delta x is going to be 1/2 in every case. And before I produce the column which will represent the area of each rectangle, I'm going to take an extra step and I'm going to develop a system to locate these heights, these special domain values. I'm going to call the first one at 1 a beginning of a list with the notation x sub 0. And then the next one will count up and be x sub 1. Then at a domain value of 2, I have the next in my list of this new notation x sub 2. At 2.5 is x sub 3. And then I finish at the upper domain x sub 4. So I've created a list from 0 to 4. Notice that my choices are integer values 0, 1, 2, 3, and 4. I'm going to represent this in my table as k values. The k value of 0 corresponds to the first important location in the domain at my lower bound 1. And my k values are going to increase by integers until we get to the last k value of 4, which is equal to the number of rectangles that I'm using in my approximation, and also corresponds to the upper bound in the interval of the area under the curve. Why did I do that? It seemed like an extra step, and it is, but this is an example of a method that is going to lead into calculating exact areas under the curve and associating the domain values, whatever they happen to be and what you're working with a sequence of integers is the step later that will allow us to get an exact area under the curve. We're not ready for it, but we're preparing for it. Now, if I'm going to include in my table a column for the areas of these rectangles, then I'm going to think of it as the product of a function value, which will be the height, and the delta x, which is the width. Symbolically, that's going to be the value of a function, but we're going to put a certain x value in, and we can symbolize that as x sub k, and then multiply that function value by delta x. The information is in the table. The values that will be the heights is this list here, 1 through 9, with k values 0 through 4, and delta x is the 1/2. So the first rectangle has a height at x sub 0, which is found by putting 1 into the function, and it produces an area of 1 times 1/2, or 1/2. The second rectangle is found by putting the x sub 1 value into my function. That's the k value of 1, which is a domain value of 1.5, which produces a function value or height of the rectangle of 2.25, multiply by the base of 1/2, and we get 1 1/8. We could speed this up. Function value times delta x, which is height times base. And then the last one at x sub 4, which is a k value of 4, a domain value of 3, which produces a height of 9, times a base of 1/2, makes a rectangle whose area is 4.5. So these are all of the areas of rectangles, this column here. And notice that there's one more than I have represented in my drawing. This last one of 4.5 is not one of the first 4. If I add these first 4 rectangle areas together, it'll be the first 4 in my table. And summing them up, sigma is a symbol that represents sum, I add these together, 3, 4, 5, 6, 7, plus 2/8 is a quarter, and then a half makes 3/4. That sum is 7 3/4. This is the sum of the rectangles that have heights at k values of 0, 1, 2, and 3. So what about this fifth rectangle? Well, it's there because there is a second way that I can choose what height to use for a rectangle area and where that height is located. This last height, the k value of 4, at a domain value of 3, is not the height of a rectangle if it's used to be the left side of the rectangle. But if I draw a height so that this value is used to represent the right side of the rectangle, and that means that it creates a rectangle that is taller than the other choice. And I can continue to use function values to produce rectangles whose function values are found by the values being on the right side instead of the left, which means that these rectangles are always higher than the curve. They produce an error that is an overestimate, and in my table, the rectangles that I'm adding together have heights that are located at k values of 1, 2, 3, and 4. In other words, it's the sum of the last 4 rectangles in my table, which produces an overestimate. And if we sum the last 4 rectangles together, we get a sum of 10 3/4. So we have produced 2 different sums. We've produced what's called a left-handed sum of 4 rectangles, all of which have heights that are based on function values that become the left side of the rectangle. And we've produced a second estimate, which is an overestimate, and those 4 rectangles are found by choosing the heights such that the function value becomes the right side of the rectangle. So we have a left estimate and a right estimate. One has an error that is guaranteed to be an underestimate because the error makes the rectangle areas below the function, and the other is an overestimate because the area or error is guaranteed to be over the values of the function. And with these 2 estimates, we can produce a double inequality that puts the exact area A in between the underestimate, in this case of 7 3/4, and the overestimate of 10 3/4. We don't know what the exact area is. The exact area is only symbolized by a capital A, but we know for certain that it is in between or within the range of 7 3/4 and 10 3/4. We would not want to average these 2 estimates to produce something that is closer, because in doing so, we would cease to know whether the exact area was under or over. There's a natural instinct to take these two estimates and average them to be more accurate. But what you lose in doing that is you lose the understanding of whether the exact area is above or below that new estimate that's produced. This method might seem overly complicated, especially when we included this different column of K and started talking about it. But this is an important ingredient because this method and using those K values is going to be what it takes to find the exact area under the curve in a future lesson.